In this video, I'd like to talk about the math question of the day for Saturday, April 22nd, 2023. And with this problem, we need to evaluate the definite integral from t-values of 1 to t-values of 4 of this expression here. So to answer a question like this, you will need the tools of calculus. This is something typically seen at the end of a Calculus 1 class. So at this point, go ahead and pause the video, see if you can work through this on your own. And when you're ready, unpause the video and we can go through this together. Now, assuming that you have attempted the problem, let's start working through it. And to answer a question like this, to answer this type of integral, we can use the power rule for antiderivatives. If, let's say, we have some function, f of x, that is a multiplied by x to the b power, and we want to take the integral of f of x dx. We'll ignore the bounds for now. We'll look at an indefinite integral. We will rewrite it as a multiplied by x to the b. We can factor the a out. We also have dx there. We have a multiplied by the integral of x to the b dx. And when actually finding the antiderivative of this, the a will just carry along, but we increase the exponent by 1. We have x to the b plus 1, and then divide by whatever that new exponent is. And of course, we would have a constant of integration since this is an indefinite integral. And this should make sense if you understand derivatives, since you can always check whether or not you calculated an integral correctly by taking the derivative of the answer, since integration and differentiation are inverse operations of each other. Just like multiplication and division, they will cancel each other out. So if we take this new function, which we can call capital f of x, and we find its derivative, so we're going to differentiate this. Excuse me, we would also have that plus c, but when taking the derivative of a constant, that's just 0. We can call this capital F prime of x. When we take its derivative, we do also have this plus 1 in the exponent. We bring the exponent down. So we have a multiplied by b plus 1. We still have the b plus 1 in our denominator. And then we decrease the exponent on our variable term by 1. So now it's just x to the b. Notice that the b plus 1s will cancel each other out. And like I mentioned, the derivative of a constant is just 0. So we have plus 0 there. And after simplifying, we get back a multiplied by x to the b, which is exactly what we started with. So this power rule for antiderivatives is very similar to our power rule for derivatives. They just work in opposite directions. But to apply this technique to this problem, we need to rewrite these radical expressions as fractional exponents, since b can be any real number here. So let me just make a little bit of room, and we can rewrite these expressions. We can start by factoring out any constants, and since we have a difference here, we can split this into two different integrals. So we can factor out the 8. Then we have the definite integral from 1 to 4 of 1 over the square root of t, or we could write that as t to the 1/2 power. Since remember, with fractional exponents, the denominator tells us the root we're taking, and the numerator tells us the power that we're raising our variable to. We're raising it to the first power, and we're taking a square root of that. Then we have minus 12 times by the definite integral from 1 to 4. We're just factoring out this negative 12. And inside the integrand, and I should mention we should have dt here. We don't want to forget our differential. Inside this integrand, we would have the square root of t cubed, but we can again rewrite that as a fractional exponent. We're raising t to the 3rd power, and we're taking a square root, and then we have dt. So now we have these two separate integrals that we can evaluate, and we'll use the power rule for that. Though when your variable's in the denominator with some type of exponent, we can put it in the numerator with a negative exponent. Or if it's negative down here, it will go to the numerator and become a positive exponent. We'll just use the basic properties of exponents there. So we have 8 multiplied by the definite integral of t to the minus 1/2 dt, and I'll just quickly rewrite this one since nothing has changed there. Now, at this point, we can use that power rule for antiderivatives. We will increase the exponent by 1 and then divide by that new exponent, so that we have 8 multiplied by t to the 1/2 power. We just added 1 to that, and we'll divide it by 1/2. Though we also need to evaluate the integral between the bounds of 1 and 4. Then over here we have minus 12 multiplied by t to the 5/2. We're adding 1 to this exponent, or 2 over 2. And then we divide by the new exponent, which is 5/2. And we also need to evaluate this one between 1 and 4. So at this point, we just need to use the fundamental theorem of calculus. And just as a reminder, let's say we have some integral of from a to b of g of x dx. And let's say that capital G of x is the antiderivative of this. So we have capital G of x. We'll evaluate that between the bounds of a and b. And when evaluating the bounds, we would evaluate our new antiderivative at the top bound, g of b, and then subtract the antiderivative at that lower bound, g of a. And again, this is just the fundamental theorem of calculus, or at least one part of it. So we can apply that here. We now have this expression, which we can simplify first. Let's get rid of this fraction here. And we're dividing by 1/2, which means we're multiplying by this fraction flipped over. We're multiplying by 2. So we have 16 times by t to the 1/2, or if we want, we can even rewrite it as a square root now, since we'll actually evaluate it, and that might be more appealing to write it as a square root. And the bounds go from 1 to 4. Then we subtract. We have 12 divided by this fraction, but that's the same as multiplying by this fraction flipped over. So we have 12 times by 2/5. 12 times 2 is 24, and we will leave the 5 in the denominator. And we have t to the 5th power, and we're taking a square root of that. And you could do that in either order. It's usually easier to take the root first and then raise it to the exponent. So we have the square root of t, and we'll raise all of that to the 5th power. Let me just make a slight amount more room, and that will be evaluated between 1 and 4. So now we can finish our integral here. Let me make just a bit more room so that we can see it. And I apologize, it's getting a bit messy, so let me just draw a line there, boxing that off. And if we continue down here, for this expression, we evaluated the top bound first. We have 16, and we could put this in parentheses and then just distribute the 16 to each. We have the square root of 4, which is 2. And then we subtract this evaluated at the lower bound, and the square root of 1 is just 1. So this will simplify nicely. Then we have minus 24/5. We can again put this inside parentheses. We'll evaluate it at the top bound first. We have the square root of 4, which is 2. We're raising that to the 5th power. Then we subtract, when we plug in the lower bound, the square root of 1 is 1. And again, we'll raise that to the 5th power. And we can simplify. 2 minus 1, that's 1. So we just have 16 here. Then we have minus 24/5 and 2 to the 5th power. If we count that up, 2, 4, 8, 16, 32. So this is 32. And we're subtracting 1 to the 5th, which is just 1. So we have 31 here. And if we compute this in a calculator or just go through the arithmetic by hand, we'll find that this is equal to minus 132.8. So this right here should be our final answer. And this is something that you can use an online integral calculator to check, or you can even use your graphing calculator if you know how to compute integrals using that. And just so that we have a way to interpret what we found, if we go back up to the original question, when finding the definite integral between two specific bounds of some function, what we're really finding is the area underneath this curve between the curve and the x-axis between these two bounds. So the area of this region, since we got a negative number, that just shows us that this function is mostly below the x-axis, but the area of that region is minus 132.8 units, whatever the units would be there.